Welcome to Web Handling. My name is Dave Roysom. I am super excited to begin a new mini-series on moisture and temperature effects on webs and rolls. Here we will cover the very wide range of behaviors and misbehaviors of web materials in response to changes in moisture or temperature. Here we will learn the effects of moisture on paper, often similar to the effects of temperature on film or foil, because they follow the same laws of physics. Finally, we will learn why measurements for moisture and temperature and other properties may not always be trustworthy. I know your time is precious, so let's get started. Moisture and temperature affect so many things that are vital for web manufacturing and end use. Things like dimensions and test properties such as strength, wrinkles and other defects, runnability, and much, much more. The reason that we can usually talk about moisture and temperature together is that often the behaviors follow the same laws of physics. The two most important are Fick's law of diffusion and expansion due to increases in moisture and/or temperature. Even so, moisture and temperature are not parallel everywhere and for every concern. For example, moisture increases the weight of paper, but temperature does not. Similarly, moisture noticeably decreases static electricity, while the reduction in static with temperature is much, much less. Still, the behaviors are often close enough so that we can often treat them the same. So, what do you need to know? What are we going to cover? Obviously, we will cover the physics of moisture and temperature effects on various materials, including material behaviors and material misbehaviors. However, since changes in moisture and temperature do not happen instantaneously, we will also need to talk about movement. In other words, how long does it take these behaviors to occur? Finally, we will make a brief mention of measurement methods. Also included there will be a stern warning to never trust any measurement that I will think you will find very entertaining. The next 3 slides deal almost exclusively with moisture effects on paper, so you may wish to skip to the next clip in this series if you have no need to learn about that. Weight, or more specifically basis weight, is an extremely important commercial specification for paper and other materials. Since moisture affects weight, we all must agree upon the conditions whereupon sample weight is measured. By international agreement across thousands of companies and organizations, these standard conditions are measurement at room temperature and relative humidity of the room of 50%. While only temperature controls might be needed for non-paper materials, paper needs humidity control in the test lab as well as moisture preconditioning of the test sample itself prior to any measurement. Sample moisture is defined as the fractional weight of water in a test sample. The water weight is obtained from differencing of wet weight of the sample minus the oven-dried sample weight. There are procedures for how to do this, codified by TAPI, ISO, and other organizations. Humidity, on the other hand, is the percentage of water that is being held in the air as a vapor versus how much water vapor that air could hold at that same temperature. Humidity is measured by many different types of hygrometers, such as the one shown here. The sling psychometer is the most accurate and trustworthy of the humidity measurements, though quite time-consuming and geeky to perform. Now that we have most carefully defined sample moisture and room humidity, we are now ready to show how they are related. The graph below shows the moisture content of a sample of a set of cellulosic material versus the humidity of the room, with one caveat. Given sufficient time, the time required to precondition a sample and how fast water and temperature move will be covered in an upcoming clip. There are many things to note about this graph. The first is that there are two curves, a wetting curve and a drying curve, both very nonlinear. Thus, we need to define upon which curve to base our basis weight and other measurements upon. By agreement, we use a room humidity of 50% on the lower or wetting curve. If the sample obtained is wetter than that, it must be first pre-dried in a 30% relative humidity chamber for a specified time and then allowed to condition for a specified time to the standard 50% relative humidity test lab environment. The second thing to note is that the curve is quite similar for most cellulosic materials, including most paper grades, but also for cotton cloth and rayon cloth and other quite dissimilar chemistries. The third thing to note is that there are three key points on the curves. The first point is the zero. This is a definition, not an actual zero moisture content. To save time, we will leave the nuanced discussion of zero for a reference article given at the end of this clip. The second point is the most important, and we've already defined the standard condition at 50% relative humidity. Given time, the equilibrium moisture content for most cellulosic materials is around 6%. Nylon and plastics also have some affinity for water, but the amount is much, much less, and thus the curve is quite different. You can find details on hygroscopic properties of both paper and film in Chapter 2 and Appendix T of the must-have 750-page Web Handling Handbook. The third point is the equilibrium content with a 100% relative humidity environment, such as you would see in a jungle, is around 20 to 24% water content by weight for cellulosic materials. Finally, a caution that this discussion and those following clips are based on water as a vapor. Water as a liquid, such as water-based coating, is another story entirely, one for which I don't feel expert enough to teach, even though I've been to many coating schools, seen dozens of coating papers presented at conferences. There are three starting points for a much more detailed description of moisture and temperature effects. The first is a 30-year-old article that I wrote while employed in paper research that still resonates today. The laws of physics have not changed much since then, and an extensive bibliography in that article is a great starting point for scholars of the subject. The second is the must-have Web Handling Handbook written by myself, Tim Walker, and Dylan Jones. Last but not least is my award-winning and trademarked Web 101 class that has been taken by about 5,000 students just like you. Here you will learn how to use material properties and the laws of physics to understand web behavior and web misbehavior. Thank you so very much for joining me in this Moisture Matters mini-series. Stay tuned for the next clip where we will discuss dimensional stability and its effect on one type of machine direction wrinkling. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. Also, please consider supporting the work of this channel using the Patreon link below. See you next time.